The second type of catalysis we're going to focus on today, we are going to see a full mechanism because I want you to see a full mechanism using a cofactor, but it's fairly simple, so I thought it was a good one for us to walk through today. We are going to see metal ion catalysis by the enzyme carbonic anhydrase. Nearly a third of all known enzymes require metal ions, so it's good for us to see an example of this today. A wide variety of metals can be used to perform catalysis. Iron in its oxidized or reduced states is going to be what we see today. Today we're going to be using zinc, but into the future we'll see iron as like the most common example. Now, these metal ions can perform catalytic functions, but they can also be structural, and this will definitely be true for many enzymes we talk about for the rest of this class. So magnesium, zinc, structural and catalytic, whereas something like manganese, iron, cobalt, those are going to be more purely catalytic in nature. Now I'm going to give us kind of a peek ahead as we begin to think about this mechanism. What are we going to see? We are going to see that this metal ion is important for binding the substrate and orienting it correctly. We are going to see in the future, but not today, how these metal ions can do a redox reaction through their own oxidation state. Think iron, Fe2+, Fe3+. Today we will see the metal ion do some electrostatic stabilization or shielding of negative charge. Something to keep in mind as well, folks. Metal ions are not pH sensitive. Last time we were together, we talked about how these R groups are going to be the best at doing acid-base catalysis when pH is near pKa. Metal ions don't have a pKa, so that is not true for them. Finally, folks, we are going to see how a metal ion can make a water molecule more acidic or more likely to give up its proton even when the reaction is happening at a physiological pH of 7.4, which is more or less neutral. So let's jump into this mechanism, folks. Let's start by drawing in the catalytic site. This catalytic site has 3 histidines that are all coordinating a zinc ion. So all 3 of these histidines are bound to a zinc ion. The enzyme carbonic anhydrase is responsible for converting CO2 released through respiration into carbonic acid. So let's bring in our substrate. But before we get to our substrate, folks, we have a second substrate of this enzyme. Which is, you guessed it, H2O. We've seen this in other mechanisms, haven't we? So the very first thing that's going to be happening in this mechanism is our zinc ion is going to polarize this water molecule. What do we mean by polarize? Well, the zinc has the 2+ charge, right? It is going to kind of pull the negatively charged, the partial negatively charged oxygen of this water towards it. And make that charge slightly more extreme, right? If zinc itself is positively charged, it's going to interact with that negative charge and kind of pull on it a bit. That's what we mean by polarize the bond. It's kind of pulling more of that negative electric charge towards it. Now, when that's happening, when the OH and the partial negative on the O is being stabilized, this water is going to be more likely to give up a proton and become OH minus. Why is that? Well, let's draw the first step of this mechanism and talk more. Elsewhere in the catalytic site, folks, we have a base. I'm not going to draw the amino acid. I'm going to put just a general base B. The first thing that happens is this base deprotonates our water molecule. That means that our base is now protonated. We'll give it a positive charge. Our catalytic zinc didn't really perform any reaction, right? But its catalytic role was to, let's draw this in now, kind of bind onto that water by grabbing onto the partial negative charge of that oxygen and polarize the bond in water, since that O minus, that partial minus, was being stabilized by the positive charge. The water was more likely to give away that proton and become OH in this step. You see how this OH now has a full minus charge? Well, that full minus charge is electrostatically stabilized by the positive charge on the zinc. So zinc's catalytic role, to bind that water, to polarize that bond so that the water can give up its proton, become OH minus. And then that zinc stabilizes the OH minus since it is positively charged. And now we can draw in step 2, folks. Don't forget our substrate, that looks a little bit like an O, was CO2. But as we release CO2 from respiration, we don't just have gas bubbles forming in our bloodstream, we are converting CO2 to bicarbonate. OH minus is a fantastic nucleophile. So it can attack the biochemist's favorite electrophile, the thing that looks like a carbonyl carbon. And you'll see that we have reached our final destination here, folks. The zinc is the first time we've seen a metal ion cofactor performing the catalytic role in a mechanism by mostly doing some charge stabilizing. So pretty cool stuff. Now we're going to move on in the next video to discuss some additional ways that enzymes increase reaction rate and act as catalysts.